Circular motion is our new topic we are going to see today. But please don't forget to subscribe to the channel. As you hear the word circular motion, circular from the word circle. So we are going to see motions in a circle or in a circular path. Okay, what do you mean by that? You see, if I have, before I do this one's going to come back later. So if I have an object P, if this one is moving around, but when it's moving in a circular path, as you see this one is moving in a circular path, as if you can see. So what we call that is what we call the circular motion. For us, we are used with linear motion. What is linear motion? When the particle is moving from here up to here, that's what we call linear motion, and that's what we've been seeing most of the cases. But now we are going to see what if this particle is moving like this. Okay, when it's moving like that, that's what we call circular motion. Okay, so that as it's moving, you see it's forming a circle. Not so, you see it's forming a circle. So that is what we have here. So it's moving around a certain point, which we are going to consider that. Okay, let us say there are many different kinds of circular motions, but under this level we are going to focus or consider two, i.e. horizontal motions and vertical motions in the circle. So that's all we are going to consider. We are going to call that. Now, when I do this, when this one covers one like this and comes back, so I started cover, then it comes back. That's what we call one revolution. So you make from here coming back to here, or from here then you come back here. That's what we call a complete revolution. And a complete revolution has 360 degrees. If you convert radians, that's what we call the 2 pi. As simple as this. So one revolution, it means that you are going to go around, then come back from where you started from. If you go the second time, now those are 2 revolutions. The third time, 2 revolutions. The fourth. So as long as you complete this circle, you are making a complete revolution or a complete turn. As simple as that. Then a quarter revolution means that, but it's that in complete revolution means that you are covering 360 degrees. So a quarter, a revolution means a quarter, you know, a circle has 4 quarters. You can divide this into 4 quarters, what we call the quadrats, but no, that's not for today. We are having from here up here is 1 quarter. But the question is, how many degrees have you moved? When I move from here up to here, have moved 90 degrees, and so I call that 1 quarter. If you move 2 quarters, means you are going to move here, then you also move here. In simple terms, you are moving 90 plus 90 degrees, which is 180 degrees, as you can see there. So it means 90 degrees is going to be pi over 4, as simple as that. Yeah, now this pi, this is the 2 pi over, because pi over 4 is 90 degrees. So let me first correct that. This is pi over 2, not pi over 4. Pi over 4 is 45. So pi over 2. So that's what they call the 90 degrees. So from here up to here, move the 90 degrees. Then let's see in here an angular speed. Now, when a car is moving in a straight line, that's what we call the linear speed. From here up to here, or some people call the tangential speed. But when you see, when I have a particle, when I move from here to this, that's the speed I'm using, or the velocity I'm using is the linear velocity. But when the particle is moving this circular motion like this, it means that it's moving with what we call the angular speed. The angular speed, as you hear the word angular, is based on the angle. So angular speed, when you move in a circular motion, we say you are moving with angular speed. Okay, a body is, a linear speed of a body is its speed in a straight line, and it's always measured in meters per second, kilometers per hour, so on. The angular speed is the speed of the body that is moving in a circular path, and measured based on the rate of change of the angle at the center. So circular path. You see when it's moving, it's creating a path which is circular. Okay. Consider body P moving in a circular path for distance AB. Now, this distance, I think now in the circles we have it. This, the wall is called a circumference. The wall, this distance from here up to here is what we call, all from here complete is what we call circumference. Now, when you move part of the circumference, what you are creating is what we call an arc. So, from here up to here, this is an arc, but when you complete, it's called a circumference. Now, we are going to consider a particle P, this particle P, moving from here up to here with an angle theta there. So P, in P, if P covers the arc in 1 second, that is if P covers the arc in 1 second, if P covers the arc AB in 1 second at a constant speed, then the angular speed, why do we call it angular? Because now it's moving in a circular path and its speed is going to be based on the rate of change of this angle. That's why we call the angular speed angular angle. Okay? So the angular speed of the body will be measured in theta radians per second, the angle which is there. So that's what we base on. So always, whenever it's in a circular path, radians per second depending on the angle, as simple as that. Relationship between linear and angular speed. Consider circular path below. Circular path below. This is the point, the middle point, or what we call the center. So this one is moving from A up to B at a constant speed of V meters per second. I mean a constant speed of V meters per second. So it's, you also have an object Q moving from here up to here. The radius of the path or the radius of the circle, which is forming the circular path, is R. If P is moving with a constant speed of V meters per second and covers AB in 1 second, then in order to get distance, to get distance, we get speed times time. So the speed at which it's moving is this. So it's covering the distance AB, or it's covering the arc AB. So the distance is our arc AB. The velocity is V times 1, which is going to be V. So the arc AB is going to be according to the velocity, the speed we are using there. Suppose the angular speed is omega. This is not W, but we call it omega. It's written like, it's different from W. That's what we call omega. Radians per second, and it covers AB in 1 second. So if this one is moving now in radians per second, why? Because the angle here is what we have, the omega. So omega radian per second from here up here in also 1 second. Okay, now if you base on the full circle here, this arc, the full arc, is called a circumference. Now, here we are trying to use an idea similar to that of the similarity, where we say big arc, small arc, a big arc, small arc or big arc. That's the idea we are trying to use. So, this arc here is the smaller arc, which is in this case is AB, as you see, arc AB. The big arc is the whole from here up to here. I know how we get the circumference of the circle. So for this big arc, it's always given by 2 pi r. That's how we get the circumference. From here up to here. Then the small angle, now the small angle here, you see it's going to be omega. This is W, it's omega. It's omega. Then the whole circle, the whole angle here, the big angle here is 2 pi. You know, if I cover the whole of this, the angle moved it from here is 2 pi, or the 360, or the complete revolution. So, you see, it's 2 pi. Now it's that big arc. We say that this arc AB, say it's V. Then it's that this pi and this pi will cancel. And so when I take this side and then cross multiply, this will have 1 times we get V. Then this and this we have R omega. So now the relationship between the linear velocity and the angular velocity is, the linear velocity is always equal to, the linear speed is always equal to the radius of the path, or in simple terms, I'm going to say radius of the sum created by that object moving in a circular path, times the angular speed. Whenever you see this, it's not W. Okay, take W, but it's called the angular speed omega. So to get the linear speed, you get the radius of the path, that is the angular velocity. Whenever you see this, angular velocity. So as you can see there. So this is just this, but this time in words. Angular speed of P. Now, look here. The angular speed of P and Q is moving in this direction also. So it's not their angular speed is going to be the same. Why is it the same? Because they are making the same angle. From here to here is the same angle. Even from here to here it's the same angle. But the linear speed from here to here and from here to here is different. This one is going to be far greater than the speed made by this particle P Q from here up to here. Their angular speed is the same because from here up to here they are making the same angle. And they say we are going to measure the angular speed in this C based on the angle it makes from here up to here. But it's this and this, they are making the same angle. So their angular speed is going to be the same. But the linear speed is going to be very, very different. Why? Because you see the arc this is making is far, this one is far bigger than the arc this is making, meaning the linear velocity for this is going to be far better or greater than for this. Okay, if a particle makes 8 revolutions in 1 minute, it means the angular velocity, the angular speed is 80 revolutions per minute. Now, so we're talking about if in 1 minute it moves 8 times or making complete revolutions, then the speed there will be 80 revolutions it has made. Then per the time it is taking to make those complete revolutions. For example, if I make 3 revolutions, 1, 2, 3, I've moved those 3 revolutions in how many seconds? Say in 2 seconds, in 3 seconds, in 1 second. So that will be the speed. So if this is the particle and then it moves like this, so you see the revolution it's making, then you also get a time. So if it makes all those 10 revolutions in 1 second, you say 10 rev per second or 10 revolutions per minute. As simple as that. So we are going to see the relationship between how is this one affecting the speed at which this is moving. And shall we see that next lesson? That's the basic of circular motions. Now we are going to see acceleration of the centripetal force and so on in the next lesson. See you there.